Hello everybody, my name is Afshin Majd and the topic of webinar for today is Harmonics in Renewable Energy Systems. This webinar is going to be a continuation of another webinar that I did on the same topic about the harmonics in renewable system. What I'm going to do today is to go over the basics and some overview of the previous webinar and also take the highlights and important points of the previous webinar and use the conclusions that we had from the past webinar, review that system, and then apply it to a new system to get the resonance point of the renewable system. The renewable system discussed here is going to be a wind power plant, including 5 or 6 turbines that I have put together very much from the previous case. So steps required to perform a harmonic study on a renewable plant would be: number 1, you need to collect all the information on the grid side, including available short circuit, X over R value for the Turbine model, and if possible a frequency scan into the network. Basically anything more than an aggregate model will help. Measurements at the point of coupling for the harmonics up to, if possible, 50th harmonic. So these are all the information that you would need in order to perform the harmonic study. So there would be a bunch of information that has to be collected on the grid side. And sometimes if you wanted to go into more details, what you can do is that you can ask the utility to provide you with the R, equivalent R and X value for each harmonic, which would be very helpful. But if not, at least for minimum, you would need X over R value and available short circuit values. And with regard to the 50th order harmonic, I'm sure you're aware of the latest update of 519/2014, which mentions that you have to cut off all the related harmonic calculations at the 50th harmonic, and you won't continue it after the 50th harmonic. So the data required from the turbines, on the turbine side, you would need some data, and those data on the turbine side would be whatever you get from the manufacturer, and you would get harmonic injection from the turbine at different power levels. So you would have harmonic injection at different power levels, including the full load. That's how usually the turbine manufacturers provide their information. So they would give you at each power level, let's say 10%, 15%, 20%, up to 100%, how much harmonic that turbine is going to inject into the grid. And the type of turbine you need to know in terms of being type 1, type 2, type 3, type 4. Type 1 being just a simple induction generator, almost no power electronic. Type 2 being a wound rotor induction generator, and some power electronics. Type 3 being a DFIG or doubly fed induction generator. Type 4 induction or a synchronous generator plus a full scale converter. Usually manufacturers should provide these test results. Harmonic results are usually based at different output power levels, and you can use the harmonic injection numbers at full load, or you can create different scenarios to perform harmonics at different power levels. So for that purpose, again, it goes back to my previous presentation, but what I can do here is that I can just bring back the EasyPower file here, and you would go to database, you would go to scenario manager, you would go to a new scenario, and I don't continue it from this point, but I can show you that from the previous example. If you remember, if you remember, we do you want to store it? I would say no. And these are the scenarios that I created from my previous presentation, and I worked with them. So you have to create them if you want to, and put different harmonic sources at different power levels here and they will inject power into the grid. But if you don't want to go into the details and look at the details of the harmonic simulation for the system, what you can do is that you can just pick the harmonic injection at the full power and use them here and do the calculation. That would be usually enough for the first run of the harmonics of your system, and doesn't provide a whole lot of details, but it's good enough usually to provide the worst case scenario. So that being said, example for a renewable plant. A plant which was discussed in previous webinars is analyzed for the harmonic spectrum, which I discussed it. Hand calculation method will be used to verify the EasyPower results. This is again the same type of work that we did before, and what it means is that once we get the results out of the harmonic module, then we do the hand calculation to compare the hand calculation versus the EasyPower results. The formula for the hand calculation will be discussed and analyzed. The factors involved in approximation of the formula also will be discussed. Now, this is a screenshot of the system that I put together before. I can just put it back here because I'm using the same system here, except for the fact that you would see that now there are these motors with the rectifiers, in fact harmonic sources being added here, which means that this part of the system you had it for your power flow calculation, and for the harmonic calculation you will have these new sources being added to the buses which inject harmonics into the system. Let's take a look at one of the harmonic sources here. We go to harmonics, and you would see that we have third harmonic, fifth harmonic, and seventh harmonic. These are the sources of the harmonic that I have used here. So for power flow purposes, you don't need them. But for harmonic purposes, I put them here, and you can copy it for all of them. If all the turbines are the same type of turbine, you can just copy them over. What it gives you is that whenever I, let's say, go back and choose this guy and activate it, and I run my harmonic, I run my summation results, and I will get the harmonic values here. So whenever it comes down to calculation of the harmonics, you can just turn them on. Otherwise, you can just choose them, go back here, and deactivate them. But these guys are going to be here to represent the harmonic injection of each turbine to the system. So this is a one-line diagram of the discussed system. This is a summary of the power flow results, and this is from the previous presentation that we had in the past. And what you see here, again, just as a review, is that the reactive power coming out of each turbine, active power coming out of each turbine, active power theoretically coming out of the plant, and active power measured at the point of common coupling. So you would have theoretically 5 turbines, each of them at 100 kilowatt, so you would expect 500 kilowatt coming out of the plant. You measure it and you simulate it in EasyPower, it gives you 492. Voltage at 1 per unit, 90% and 110%. So these are the reactive power at the point of interconnection without the compensator and with compensator. And again, we went into details, really small details of simulation for this system, and eventually it gives us the required cap bank size, which again was closer to 1.2 MVR. So let's assume that there is 1.2 MVR cap bank there already. It's going to be added either to this point or to this point, and it's already in the system. We calculated it. Let's just move on to the next step, and we already have added the sources, equivalent sources of harmonics instead of those turbines, and we simulate the system, see how it looks like. So as you saw, this is the frequency spectrum, the harmonic spectrum of the turbine that we added, third, fifth, and seventh, and I put them in my system, and these are the percentage of the harmonic. These are just example numbers that I have put here, and we already saw them in EasyPower. There is a very effective and important formula in short circuit calculation for the transformer short circuits, and that's I short circuit equals kVA divided by square root of 3 Z% base kV, and that would be in amp. On the immediate secondary of any step-down supply transformer, the maximum symmetrical short-circuit current can be estimated. That's how you would estimate it. Given the transformer kVA rating, nameplate, percent impedance, and secondary voltage base, the short-circuit current on the low voltage side of the transformer in amp is going to be this value. So this is the value that you would use to calculate the short-circuit value on the secondary of a transformer. Parallel resonance circuit. So if you have, let's say that you have a system which has a utility, has a cap bank, very much like the system that you saw here. And there's a cap bank already here. So parallel resonance circuit. So you have a harmonic source here. You have the utility source and you have a cap bank. Then this would be the equivalent circuit of this system. And in order to see where we will have the resonance, to analyze this network, we simply parallel the two impedances together. So if you wanted to simple parallel these two systems together, what you would get is that XL and XC being in parallel is going to give you this result. And let's see if there would be a harmonic at which XL and 1 over XL and 1 over XC are going to be equal. From the modeling section, we know that XL is 2 pi FL, XC is 1 over 2 pi FC, XLH is this value, and XCH is this value, which means that at different harmonics, you're gonna have higher reactance, and for the capacitance, you're going to have less capacitance. Now, in order to put the equations equal, XL fundamental, and if I put in fact the XC and XL equal, what it means is that this value, these two are going to be equal. So that means that if these two are equal, then H is going to be equal to a square root of XC fundamental divided by XL fundamental. That's where we are going to have the resonance. So let's just simplify this formula and see what it gives to us. This would be a more useful form of the same formula, H. And as you see, it's the cap bank kVR divided by transformer kVA rating. Let's see how this formula was derived here. If you wanted to do hand calculation, H equals a square root of XC fundamental divided by XL fundamental. This is equivalent to this number, which I have divided the numerator and denominator by Z base. And it's going to give me this value in per unit. Z base is going to be V squared divided by S base. This is going to give me a square root of 3 kV ln and transformer kVA rating divided by 1000. This is Z base. In fact, it's just simple V squared divided by S. I simplify it. I get this formula here. And for XC fundamental divided by Z base, I'm going to replace this value here, and this is the X or the capacitor bank kVA reactive or kVAR. So that's going to give me, in fact, if you simplify it, factor out 3000 from the numerator and denominator, and you're going to get this value. Once you get this value, now let's just simplify the original formula that I had here. This guy divided by Z base is basically the transformer impedance in percent, and this value divided by Z base we calculated here, and it's going to be equal to this value. So it's going to be 1 divided by Z percent times cap bank kVR divided by transformer kVA rating. So that if I go back here, you will see that this is the very same formula here. So that was just a proof of how we can just develop this formula and where it comes from. Now I continue, and let's just go back to our EasyPower file, because this is the time that we can do some verification in terms of the formula and look at the resonance of the system. Just for those of you who may not be maybe familiar enough, or you might have forgot this function, you have to switch to Harmonics once you build your system, and choose the bus that you want to perform the frequency scan from, and scan and look at the value, which would be the resonance of your system from that bus. So it means that somewhere closer to 11th harmonic, you are going to have a resonance around here. Let me move this guy out of our screen here, and this is a screenshot of the same resonance for the system. Our system has a resonance at 11th harmonic, which means that you try, and you should try, to either move this resonance frequency or make sure that none of the sources have any injection at the 11th harmonic. And what it means is that you we can go back to all those sources one by one, look at them, and make sure that none of them is going to inject any 11th harmonic to the system. And as you see, we have third, we have fifth, and we have seventh, but we didn't have any 11. So for the sake of this example, maybe we are fine, but usually having resonance around 11, 5th, or 7th, these are kind of red flags. You always try to push the resonance frequency to higher frequencies where it's very or less unlikely to have any harmonic injection. In terms of the hand calculation, the formula will give us hand calculation value a square root of 1 over 7% times 1.2 divided by 10, or almost 10.9 order. So that's where you would get the resonance from the hand calculation value versus 11 point or 10.9 here. Let's just go back here, 10.7. So this is EasyPower result, this is the hand calculation result, and you see that there is a good correlation. The values are almost close to each other. There is a good correlation between the EasyPower results and hand calculations. There are approximations, which makes one of those approximations, in fact, is that we neglected the value of R. We neglected the value of the R, and if you deal with X over R high, X over R values, you're okay. If X over R value is a small value, then there are issues there. Almost all the renewables are sources of the harmonics injection. The system has to be checked for the resonance frequency. The dominant frequency in the system should be away from the resonance. Due to existence of cap banks, we can tune it to filter out unwanted frequency. So for the cases like this case that you already have a cap bank in your system, you can tune them always in order to get rid of the unwanted frequencies. Keep in mind that whenever you add a reactor to a cap bank to tune it, in fact, you are impacting the reactive power capability of the cap bank. So that's one extra calculation you have to make sure you do. The other thing is that when you do the frequency scan with the cap bank alone, and then you add an inductor there, and you do the frequency scan again, you would notice that the pole has shifted. And if the pole has shifted, then you may sometimes need to revise some numbers. So what it means is that if you add an inductor and you see that the pole value has changed in that system, it means that just make sure that it doesn't fall on top of a already existing harmonic. So we try to get rid of some harmonics, and we try to tune the cap bank to filter them out. We have to keep in mind that this is going to already change some other poles in the system. So it's worth to go back and look at everything again, making sure that nothing has become worse. But it's correct that you just filter out some harmonics, but you might actually have shifted some poles around, which might make the situation worse. So you have to revise those numbers too. And eventually with this slide, I conclude the presentation. That's the end of the presentation. What we covered here was in fact the continuation of another webinar that I had done in the past. So I put the same system together. I came up with a formula, which is a popular formula in the harmonic system. I used EasyPower to calculate the resonance frequency of the system. I did my hand calculation, compared two side by side, and that gave me a good confidence that the systems and these numbers correlate very well. And I will go into more details probably in the future examples and webinars, but for now I just wanted to make the point that if ever you wanted to perform some studies applicable to renewable system, in particular wind systems, that's how you would pursue, that's how you would do that. And then also you have a strong formula, a good formula, reliable formula that you can use just to verify your results. I hope you guys use it and find it useful for your harmonic calculations. For any question, you can certainly reach out to me and ask your questions or email the questions to us, and I will be happy to answer that, or you can just contact us, call us, and just ask to speak with me. Other than that, I hope that it's a very useful source for harmonic calculation. If there are studies, engineering studies, and you want us to help you with that, again, I will be happy to help. With that being said, I conclude the presentation. I wish all you guys a very good day. Thanks.